Alright, in this video we're going to look at a problem that deals with accumulation and rates of change. Those are kind of the two major broad ways that we apply the integral and derivative respectively. We know the derivative is the instantaneous rate of change and that the integral of a rate of change is equal to net change. And when we talk about net change, that's where we're talking about accumulation. That's what I mean here is we're talking about as things accumulate, that's the net change in an amount. Okay, and we're going to see that applied in an example here, and there's lots of, this is a really common type of application on the AP exam as well. So here's a question from 2017, number 2. It says, when a grocery store opens, it has 50 pounds of bananas on a table. Customers remove bananas from the display at a rate modeled by f of f equals 10 plus all this nonsense. So for 0 to 12 hours, we'll see, per hour, where f is measured in pounds and t is the number of hours since the store opened. So for the 12 hours that the store is open, this is the rate at which bananas are leaving the shelf. It's important to distinguish that that's not the amount of bananas that are leaving the shelf, that's the rate at which they are leaving. After the store has been open for 3 hours, an employee will add, or employees add bananas to the display table at a rate modeled by G, where G is measured in pounds per hour and is the number of hours after the store opened. So first thing I'm going to do before, because I see that this is number 2 and that this is a calculator active question, I'm going to start by just entering the functions into my calculator before I do anything else. Okay, so I'm going to pause real quick and then enter those into the calculator for us. Okay, so we've got both the functions entered into the calculator. It's important to be really careful and deliberate that you're entering the function in as exactly as you see it on the exam. Okay, so make sure you double check it and that they are accurate. I've also, again, entered everything in terms of t, since that's the variable as it was defined in the problem. Okay, and I've named them f and g just like they are in the problem. So f, remember, is the rate at which bananas are leaving the shelf. G is the rate at which bananas are going onto the shelf after 3 hours have passed. Alright, so let's go back to the problem and let's see what we're being asked. It says, how many pounds of bananas are removed from the display during the first 2 hours that the store is open? How many pounds is saying the net change in bananas on the shelf, right? Bananas are leaving the shelf. We want to know how many bananas leave the shelf over 2 hours. This is net change. And we know that the integral of rate of change is net change. So since we're talking about bananas being removed, this is going to be the function f. So all we need to know then is the integral of that function f. Since f is the rate that bananas are leaving the shelf, this is the integral of rate of change. And we want to know it for the first 2 hours that the store is open. It opens at 0 hours. 2 hours later would be t equals 2. So this is the integral that we need to find from 0 to 2 of f. And now we can go over to the calculator and find the integral from 0 to 2 of the function f, which is a function of t. And there's our integral, 20.051 to 3 decimals. Okay, if we want to indicate units, this is pounds of bananas that have been removed. Okay, they don't ask us to interpret it since the question is asked, gave us the interpretation. This is the number of pounds of bananas that are removed from the shelf in the first 2 hours that the store is open. Okay, so the first part's really simple and straightforward. On to the second part. Part B asks us to find f prime at 7. Using correct units, explain the meaning of f prime. So let's start by finding f prime. That's very simple. That's an instantaneous rate of change. That's the derivative at a point. So we can go back to our calculator and find this very simply. This is a derivative at a point, and we want to find it on the variable t at a value of 7, and we're finding the derivative of f in particular. We wanted to know f prime at 7, so derivative of f at 7 equals negative 8.1195. So if you round, that'd be 0.1120, excuse me, 0.120. If we truncate, it'll be 0.119. Both answers are completely correct. Again, since I like to round, we'll say 8.120. Okay, now it says explain the meaning in context of the problem. Well, this is F is the rate of at which the bananas are leaving the shelf. F prime is the rate of change of that rate. So what this means is 7 hours after the store opens, right? That's what t equals 7 means, 7 hours after store opens. The rate at which bananas are leaving the shelf that is the thing that's changing. So this is the rate of change of that rate that bananas are leaving the shelves. So this rate that bananas are leaving the shelves is changing at a rate of negative 8.12. So we can say that that rate is decreasing by 8.1 pounds per hour. Per hour. We actually need to. I wasn't repeating myself there. The rate is in pounds per hour, and it's changing per hour. So we do actually need to write this twice. So in other words, or to say it in one shot, 7 hours after the store opens, the rate at which bananas are leaving the shelf is decreasing by 8.12 pounds per hour per hour. That is, every hour the rate decreases by 8 pounds per hour. Okay, so kind of a confusing answer to have to explain there. So at least make sure you're definitely getting that point for the derivative. And in this case, again, it's the rate of a rate. So it has this sort of redundancy that makes it a little confusing. In part C, it says, is the number of pounds of bananas on the display table increasing or decreasing? This question is a little bit weird. It's related to calculus, but you're not going to do any actual calculus computation. What we're going to think about is the total number of bananas on the shelf, or total pounds of bananas on the shelf, goes up if we are adding more bananas than we're taking off, and it goes down if we're taking more bananas off than we're putting on. In other words, what we really want to figure out is, are we adding more bananas or are we taking off more bananas? And that'll tell us whether the total is going up or down. So we know that the bananas being added are modeled by the function g, and the bananas being taken off are modeled by the function f. So at 5, we'd want to know what is the rate at which we are taking bananas off of the table. So we just need to know what's f of 5. Again, we don't actually have to do any calculus computation here. That's 13.8, 13.795 was it? So 796 rounded. And then what is the rate at which we're putting bananas back on the shelf? And that's 11.533. And what matters here is f of 5 is greater than g of 5, which means we're taking bananas off faster than we're putting them on. Therefore, the number, or the number of pounds of bananas is decreasing. At 5 hours after the store opens. Okay, because again, the rate that we're taking bananas off is greater than the rate that we're adding bananas on. So more bananas are leaving than are going on, so the total number of bananas is decreasing. Okay, so you're going to get a point here for thinking about these two guys, and then a point here for correctly coming to the conclusion that they're decreasing the amount of bananas on the shelf. How many pounds of banana are on the display table at time t equals 8? All right, let's think about this. The store opened with 50 pounds of bananas, right? And after the store opened, or I think in general here, we want to take the initial amount that we had, and we want to subtract amount removed, right? People are taking bananas off the shelf all day. And then we want to add the amount that are put back on by the employees. So, or you could say amount replaced. So the initial amount minus what was taken off by customers plus what was added on by store clerks is going to give us the total amount that are on the shelf at t equals 8. Well, the initial amount again was given as 50. The amount removed, well, we have a function that tells us the rate that bananas are being removed at. That's f. This was t. And if we want to know the total amount removed, then we need to take the integral of t from 0 to 8. That'll tell us how many bananas were removed from 0 to 8 hours. And similarly, we have a function that tells us about the rate that bananas are being added to the shelf, and that's g of t. If we take the integral of that from 0 to 8, that will tell us the amount of bananas that were added back to the shelf from 0 to 8 hours. Except, one careful thing. We were also told at the beginning that they didn't start adding bananas back to the shelf until 3 hours after the store opened. So we can't take the integral from 0 to 8 because they weren't adding shelves in the first 3 hours. We have to take that integral from 3 to 8. Okay, so super careful, pay attention to details there. Really easy to miss that. Okay, so then we can just type this into the calculator and we'll be able to find our amount of bananas on the shelf. So we started with 50. We subtracted the amount that were taken off the shelf. That's modeled by the integral from 0 to 8 of f of x, f of t. That's the amount taken off the shelf. Then we want to add the amount that was put back on the shelf, which is modeled by the integral from 3 to 8. They didn't start adding bananas until after 3 hours. And the model for bananas added was g, so g of t. Okay, and so here's our integral just as we wrote it in our notes. And that's our integral 23.347. So we could say that there are 23.347 pounds of bananas on the shelf 8 hours after the store opened. All right, good. So there's a really good, pretty clear example of how we can use accumulation functions and use the integral and the derivative to figure out rates of change and so forth. So there's a good example of a common type of AP question.